So last time we talked about whether a sequence converged or diverged, and today we're going to be starting our list of series tests. Now, if you remember from last class, I mentioned that these are going to be the tests that we use for series. Now, as a general review, I want to remind you that a sequence is going to be a list of numbers separated by commas. So like 1, 1/2, 1/4, so on and so forth. When we talk about a series is a sum of those numbers. So now we're talking about 1 plus 1/2 plus 1/4 plus ... Now, a series convergence and divergence is completely different from a sequence convergence and divergence. And we mentioned that last time when we looked at this example right here. We said here is a sequence, and this sequence converges. It looks like it's converging to 4. But if this was a series, say 3.5 plus 3.75 plus 3.89 plus 3.95, this series would diverge because we are never going to actually get to a summable amount. Okay, so really important that we learned last time that if I want to test to see if it converges or diverges, we took a limit of the a sub n formula. But for series, there's going to be multiple tests that we will use to determine if something converges or diverges. So to start off those tests, these are our tests for series. Really important that you understand the difference. These are for series only, okay? The first of those tests that we're going to encounter is called the geometric series test. And as it suggests in its name, we are only going to use this for geometric series. Like we learned earlier, geometric series tend to follow the form, the sum, from n equals 1 to infinity of a1 times r to the n minus 1 power. It can also follow the sum from n equals 0 to infinity, a sub 1 times r to the n. So what's the difference? Here we see the indexing starting at 1. Here we see the indexing starting at 0. The a sub 1 is the same in both of these. So both of these are geometric formats. I don't want you to get thrown off by this, but basically you could see an exponent of n minus 1 or an exponent of n. Now remember, when we talk about a sub 1 is the first term of the series, and r is our common ratio. So the geometric series test says the series is going to diverge if the common ratio is greater than or equal to 1. If the common ratio is less than 1, that series is going to converge. And in fact, not only does it converge, but it has an actual summable amount. The sum of an infinite geometric series is a1 over 1 minus r. You need to know that formula. Really important. Okay, so let's do a couple of examples. Now, what I would caution you in all of this is to remember that sometimes it becomes a little bit difficult to see a1. So to the side, I want you to write yourself a note. Be careful, because sometimes you can't see a sub 1 in the formula. Let me give you an example, okay? So we look at example number 1a, not obviously geometric, but remember I told you, when in doubt, list out some terms. So let's list out some terms of this series. If I list out some terms starting at 1 to infinity, and you'll notice this does not look like this format right here, because it says if it's supposed to start at 1, I'm supposed to be an exponent of n minus 1. It is. Let's plug in 1 into our formula. If I plug 1 into this formula, I've got 3 over 2 to the first power. If I plug in 2, I've got 3 over 2 to the second power, or 3/4. If I plug in 3, I've got 3 over 2 to the third power, so 3/8. And so here's my series. Important to note that I can tell right off the bat that this is geometric and that the common ratio appears to be 1/2. And I can see my first term, a sub 1. So ultimately then the question becomes, well, why didn't it look geometric? Why doesn't it look like these two geometric formulas up here that it says it's supposed to look like? Here's the answer. I could actually rewrite this thing by saying start at 1, stop at infinity, take out the 3, leave your 1 over 2 to the n, okay? Let's keep our rewriting process. I'm going to move this stuff out of the way just a little bit. And now let's go, hey, you know what? Technically, this is 3, and 1 to any power is 1, so let's call that 1/2 to the n. Now, I could really easily make a very, very serious error here. If I look at this, it looks like the first term is 3. Guys, the first term is not 3. The first term is actually 3/2. Because if this starts at an index of 1, technically the power is supposed to be n minus 1. So how do I make that happen? I'm going to shrink this one more time and move it out of the way. And let's do a little bit of work. What if I take out another 1/2 from this? This is going to become 1/2 to the n minus 1. Now you're like, Miss Ari, how did you do that? How did you do that? Well, I did that because technically this is 1/2 to the first power. And 1 plus n minus 1 is n. So all I did is I pulled it apart. And it becomes fairly obvious to see now my formula is n equals 1 to infinity of 3/2, 1/2 to the n minus 1. Now students always get freaked out. They're like, Miss Ari, am I going to have to do this? Am I going to have to pull geometric series apart to make it look like my two versions up here at the top? And the answer to that is no. Technically, all you need to be able to do is recognize it's geometric and recognize the first term and the common ratio. That's all you need to be able to do. Why am I showing you all this? I'm showing you this because I don't want you to make the mistake of telling me that the first term is 3. Because students often will look at this version right here and they go, oh, the first term is 3. The first term is not 3. So what should you do? You should list out some terms if you're not sure. So I've got this now written in its form like I wrote it up in the top box. Let's actually make a conclusion. It becomes easy to see that the common ratio is 1/2. You need to tell me that common ratio is less than 1. According to the geometric series test up here at the top, if the common ratio is less than 1, the series converges, and here's where you're not going to like it, by the geometric series test. You have to say by what? So some things I'm looking for. I'm looking for the common ratio, the comparison to 1, the conclusion, by what test. Let's do it again. If I look at the next one, remember, when in doubt, list out some terms. So let's list out some terms. I could sit here and I could plug in 1. If I plug in 1, why 1? Because this says it's going to start at 1. I've got 3/2 to the first power. That's going to be 3/2. Then I plug in 2. 3 to the second power is 9. 2 to the second power is 4. Then I plug in 3. I'm going to get 27 over 8. And I'm going to ask myself, is this geometric? Yes, it's geometric. And I don't need to do anything else to prove that if I don't want to. This is enough to go, okay, it's geometric. Well, how do I know that it's geometric? It looks like every single time I am multiplying by 3 over 2, multiplying by 3 over 2. Therefore, my common ratio appears to be 3 over 2. Okay? So if my common ratio is 3 over 2, I could go right to the conclusion. I can say R is equal to 3 over 2. I need to make a comparison to 1. That's greater than 1. Therefore, the series diverges by the geometric series test. Now, something you might be wondering. Why doesn't this look like the two formats up above? Remember, the two formats up above says if the index starts at 0, then this should be A1 times r to the n. If the index starts at 1, this should be A1 r to the n minus 1. Well, check it out. This index starts at 1. Why isn't this power in n minus 1? I can make it a power of n minus 1. How do I do that? I am going to take out a 3 halves. If I take out a 3 halves, it is now 3 halves to the n minus 1. Why? Because there's 1 here, and there's n minus 1 here. And remember, 1 plus n minus 1 is n. So basically, I'm unfolding it. Now, it looks like this format, and I can see here is my A1, here is my common ratio. Now, do I need to do all this? No, you don't. As long as you can recognize what the common ratio is, that's the only important thing. Now, if it converges, you could be asked, what does it converge to? So let's go back to this formula. The sum is A1 over 1 minus r. Guys, I can actually tell you that the sum of this series from 1 to infinity of 3 over 2 to the n will add up to first term, 3 halves, 1 minus common ratio of 1 half. That's going to give me 3 halves over 1 half. Remember, dividing by a fraction is the same thing as multiplying by the reciprocal. And I get 3. Guys, the sum of this series is 3. If you add up every single term, you're going to get 3. An infinite series is going to sum to 3. Okay? So you're going to get a lot more practice with this on your homework, and I want to go ahead and go to our second test of the day. And this second test is called the Nth Term Test for Divergence. Guys, I want you to notice that it says divergence. This test can only be used for divergence. This test will never prove convergence. This test will never prove convergence. Only divergence. So here's what it says. If you take a limit as n approaches infinity of the a sub n formula, and it is not equal to 0, then the series is going to diverge. Now, why does this make sense? Okay, let's think about, for example, something like, the series we just had above. 3 halves plus 9 fourths plus 27 eighths plus ... If the terms that are out here, way out here, are not going to 0, then I'm going to keep adding on stuff. And if I keep adding on stuff, how can it possibly have a sum? Now, some important things to know. What if you do this test and you do get 0? You cannot say the series converges. Getting 0 is actually inconclusive. So if you get a limit that's equal to 0, this test is inconclusive. You might want to highlight that. Okay? So how do I use this test? Okay? Remember, this test can only be used for divergence. So here is a series. When in doubt, let's add a couple of terms. Let's see what happens. 2 times 1 is 2. 2 plus 3 is 5. How did I know to start at 1? The index starts me at 1. Okay. 3 times 1 is 3. 3 minus 5 is negative 2. Let's go to the second term. 2 times 2 is 4. 4 plus 3 is 7. 3 times 2 is 6. 6 minus 5 is 1. Third term, 2 times 3 is 6. 6 plus 3 is 9. On the bottom, 3 times 3 is 9. 9 minus 5 is 4. And so this isn't geometric. It isn't arithmetic. We just have something interesting that's happening here. So to perform this test, you need to take the limit of this formula. What are we doing when we take this limit? When we take this limit, we are basically deciding what are the terms that are way out here at infinity doing. Okay? Now, when we talk about infinite terms, this and this, they're not really doing anything. So since they're not doing anything, I can say that this limit is equivalent to this, which is going to give me 2/3. So what does that mean? As you get way out here towards infinity, these terms are going plus 2/3, plus 2/3, plus 2/3. How can I have a sum if I keep adding 2/3? You can't. You can't have a sum if I keep adding 2/3. Okay? Now, is it really exactly 2/3? No, but it's approaching 2/3. So what do I want to say to make this conclusion? I want to say this is not equal to 0. Therefore, this series is going to diverge by the nth term test. Okay? So basically what we're saying is this means the terms as n approaches infinity are approaching 2/3. And those are not small. And since they are not small, this means this will have no sum. Remember that a series is a sum. Okay? Let's do one with a factorial. Let's say you get something like this. Remember, it's important. If you don't know, list out some terms. I'm going to skip this step for now. We're going to go right to the limit. And we're going to take the limit as n approaches infinity. Important to note that this 2 is not within the factorial. So I have n factorial over 2n factorial plus 1. As we go out towards infinity, this plus 1 isn't really doing anything. So that means that this is now equivalent to the limit as n approaches infinity of n factorial over 2 times n factorial. And I can think about this as those n factorials are going to get rid of each other, if you will. And so what I'm left with is 1/2. And that means this does not equal 0. Therefore, my series diverges by the nth term test. What am I looking for when I'm grading problems like this? I need to see does not equal 0. Therefore, it diverges by what test? Okay? So that means is as I'm plugging in terms here into this series, as we go way out here, like out towards infinite terms, these terms are basically going plus 1/2, plus 1/2, plus 1/2. They're not getting small. Therefore, it can't have a sum. Okay? I've got one a little bit interesting maybe for you to try. So I would like for you to press pause and give this one a go. All right, now that we're back, let's list some terms. Let's list some terms. We're going to plug in 1 because that's where the index starts. 3 to the first power is 3. 3 minus 2 is 1. And 3 to the first power is 1 on the bottom. 3 to the second power is going to be 9. 9 minus 2 is going to be 7 over 9. 3 to the third power is 27. 27 minus 2 is 25. 3 to the third power is 27. And we're going to keep going forever and forever and forever. Now, this is not geometric. It kind of looks geometric because you see that the denominator is growing by powers of 3, but not the numerator. So let's take a limit as n approaches infinity of 3 to the n minus 2 over 3 to the n. Now, out towards infinity, this minus 2 is going to do nothing. So this is equivalent to the limit as n approaches infinity of 3 to the n over 3 to the n. Well, that's going to give me 1. And 1 is not 0, which means this thing does not get small. Therefore, my series diverges by the nth term test. So basically what's happening is way out here towards infinity, I'm basically going +1, +1, +1. How can it have a sum if I'm never going to get small enough to be an actual sum? Okay, so my infinite terms are basically approaching 1. You can kind of see that right here with the 25/27. Okay, now the third test that we're going to cover is probably one of my favorite tests, and it's called a telescoping series. Because if I have 1 minus a half, and that's negative, and this is positive, and then I have a +1/3 and a -1/3, eventually there's going to be a -1/4 and a +1/4, and this thing is going to collapse on itself. Now, some things you should know. This is not an AP topic, but you can use this on the AP exam. A telescoping series is called a telescoping series, and I'm going to draw a really bad example of this, because if you think like, if you've ever watched Pirates of the Caribbean, like the old, like spyglasses that they used to have, you know how you'd have this spyglass, right? And the spyglass would basically start off, and then the next one would get like a little bit bigger, and then the next one would get a little bit bigger, and this thing would like fold up and completely collapse. Like if you ever watched Pirates of the Caribbean, Johnny Depp like looks through his little spyglass and then collapses it up. That's what this series is doing. So it is not obvious that you have a telescoping series until you actually start listing out some terms. So I want you to think of this not so much as a test, but as behavior. Okay, so let's say I have this series right here. Let's actually start by listing out some terms, and that's always going to be my suggestion. When in doubt, list it out. Okay, when in doubt, list it out. So if I plug in 1, why 1? Because our index starts at 1. I got 1 over 2 times 1 is 2. 2 plus 1 is 3. 1 over 2 times 1 plus 3, that's 1/5. I can go to my second term. 1 over 2 times 2 plus 1, that's 1/5. Minus 1 over 2 times 2 is 4. 4 plus 3 is 7. Go to the next term. 1 over 2 times 3 plus 1, that's going to be 1/7. 1 over 2 times 3 plus 3 is going to be minus 1/9. And basically, this pattern is going to continue until we go on forever and forever and forever, continuing in this form. Plus dot, 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 plus dot, dot, dot. So if we notice, I can tell there's a minus 1/5 and a plus 1/5. And there's going to be a minus 1/7 and a plus 1/7. And eventually, even though I didn't list it out, there's going to be a minus 1/9 and a plus 1/9. And so essentially what I now need to prove is I need to prove that this thing is getting really, 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 really small. And what's left? Well, what's left is going to be this 1/3. Guys, this series actually converges to 1/3 because it's going to keep getting rid of itself, and there's only going to be one value left, just 1/3. So basically what's happening is this series collapses and converges to 1/3 by the telescoping series test. Now you will see some books that will actually take limits of these n terms here, and that's an appropriate thing to do. It's not going to be required because again, this is not AP tested, But let me just show you, if you were to take a limit of these end terms, 1 over 2n plus 1, you'll notice those are getting small. And this limit also of the n approaches infinity of 1 over 2n minus 3, that's also getting small, which is why I can guarantee that all that's going to be left here is just the 1/3. Okay, so we're going to stop there. You will have another video to watch after this for P series, so don't forget that, and I'm going to stop.